Welcome to the video on stochastic differential equation, in particular on linear stochastic differential equation. All right. So this is chapter 5 in the lecture notes. So before coming to the linear case, I would like to give you the general definition of what we understand of a stochastic differential equation. So stochastic differential equation. And well, most of the time I will use the shortcut SDE is of the form. So I have a stochastic process X, and its evolution is given by a, here say, deterministic function mu, depending on time and the process itself with respect to dx, dt, plus a function sigma, depending on the process X, and then integrated with respect to the Brownian motion. And this here, I mean, of course, this says a priori, I mean, these differential operators are not well defined, as we already discussed in the introduction. So we need to give a meaning. So this is just a short writing for actually the integral equation so we integrate formally both sides in time. So if we integrate the left-hand side in time, we get just xt, and then the right-hand side becomes, I have to assume that there's an initial condition. So that I start at a point x0, which is a constant. And then I integrate from 0 to t of mu ds, with respect to ds. And then I have the stochastic integral of sigma with respect to the Brownian motion. All right. So this here, like this integral equation has a meaning, right? So this is a Lebesgue-Stieltjes integral. This is an Iter integral, and then this equation is well defined a priori. I mean, it's not clear that we have the solution yet, but this is what we want to investigate in this section or in the chapter, is to understand under what conditions here has this differential equation a meaning. And then differential equations are used to model evolutions in different fields like engineering, financial mathematics, social science, and so on. So this is just a very general model of dynamics in the real world. So just to fix some language here, so this mu is a function from 0 to t from r to r is called drift function. Why is it called drift function? Because if you take the expected value of this differential equation, right? I mean, if sigma is 9, this is a martingale, so this disappears, and so the drift of the dynamical system here, or stochastic dynamical system here, is given by mu. Sigma is also a function from 0 to t, from r to r, is called volatility or diffusion function. So in finance, this is usually called volatility function, or in probability theory, it's often called diffusion. So this gives you somehow a scaling of how heavy the solution G fluctuates, right? Because the Brownian motion is described the noise of the system. Right. And 0 is just a real number, is the initial condition. This is where the system at time 0, we are at x0 is equal to x0 value. This drift, volatility, drift function, and this is a stochastic differential equation. Okay, but if you see, if you set sigma to 0, right, this term just disappears, and we have the classical ordinary differential equation, right? So, stochastic differential equation are nothing else than the stochastic generalization of ordinary differential equation. Okay. So I mean, the goal is to study this. Study this equation. And you often see, I mean, this writing, but this shorthand writing means just we consider this integral integration. And right, if you cross away this and take the derivative, I mean, this is exactly what we wrote here. All right, and let us start simple by focusing on what's called linear one, and this means that the coefficient mu and sigma are linear, or at least are fine in the solution process X. Okay. So this brings us to chapter 2.1, which is the purpose, I mean, the focus of this video, linear SDs. Okay. So let me start with some examples before then coming to the general theory. So example 5.1. So these are two linear stochastic differential equation, which you might see. So the first one is the dynamics. If you do finance, you will see this equation rather often. So you have a mu, which is just a constant, so we keep it simple. And the sigma is also just a constant. I mean, it's not constant, it's a linear function. So right, this is a really linear function. So mu and sigma are linear functions in xt. They by motion, and once you start your dynamical system from some positive, so you have a drift coefficient and volatility constant, right? Volatility parameter. So this is mu is r and sigma is positive. Okay, and now we want to solve this equation, right? We need to find a solution. Oh, I forgot to define what the solution is. Let's here we go. So sorry for that. I didn't tell you what the solution is. Now I want to tell you. So stochastic process X is called a solution of the SDE. Okay, let's give it a number, 5.1 of 5.1 if, well, X is in H2 log. So we want that this, I mean, the solution ensures that the stochastic integral and the Lebesgue-Stieltjes integral are well defined. Is a continuous process, right? I mean, it has to be a continuous process because the right-hand side is continuous process. And we want that it satisfies the given integral equation 5.1. All right. Okay, so let's come back to here a simple linear SDE. So we want to find this process X. To find, and well, this is, I mean, the same as if you just solve ordinary differential equation or partial differential equation. If you want to solve it, you need to make a smart ansatz, or yeah, have an idea. So to find xt, we make ansatz so that xt is given as a function f, and f is the deterministic function depending on time and the Brownian motion. So we say, I mean, these are the input parameters. We hope that we are lucky in this simple situation that a solution is just given by a function depending on time and the Brownian motion. For some f depending on time, space, right? And now we need to find this function f with the hope that it exists. All right. Okay. So if we have this structure, the great thing is that we have Ito's formula available. So by Ito's formula, so let's apply Ito's formula to see what we get. What do we get? So let's use this short writing. So fx is, right, this is here. And I want to have the short writing because, well, that makes our life simpler. So this is, and here I can now apply Ito. So what is Ito telling me? Well, Ito is telling me that the time derivative, and I have the space derivative. This is space-time Ito formula as we have derived. And I have 1/2, so the term from the quadratic radiation. And here, just using, if you integrate both sides, if you look at the integral expression, this is exactly the space-time Ito formula. So, and now let me rearrange this a bit. Sorry, this is dt. So let's put all the dg terms together. So we have here 2.5 g t, right, plus the stochastic integral term, which is this here. All right, and now I want to have f in a way that that this is equal to, so this is not a quality, so this is what I want to have. I want that this is equal to the FDT. Right? This is because x should be a solution to my equation here. So that's my hope. This is nothing else plug in. So this is f e t plus f e t. Right. All right. But now we know that this here is an E2 process, and this here is an E2 process, right? Well, if these are both are E2 processes, we can match the coefficient, right? So the coefficient of the Lebesgue integrals has to be the same as these, and the coefficients appearing in their stochastic integral, they have to be the same as well. All right, so what does this mean? Matching the coefficients. What do we get? Okay, wait. So we know that mu f, right? This is this here, the first term, has to be the same as here, the derivative in time, and then 1/2 the derivative in space, twice in space. And the same for the stochastic integral part. So we have here sigma f has to be the same as fx. Right. Okay. But this here implies, and this is why I like it, that f on x, right? I mean, we know this ordinary differential equation, and this can be solved by the exponential function. Sigma, where you get here sigma g, and then we have now, can shift it by a function g. Suitable g function g. Okay. Okay. And now we plug this, this expression here into the first equation. So what we get, we get g squared. This is here, the time derivative of this f, plus sigma squared. F, right? If I take twice the derivative space here, so if I take twice the derivative of the exponential function, still the exponential function, so I still have here my f, and this is equal to mu times f. And this means, since f is positive, right? This is a positive function, I can divide by f. So I have g prime is equal to mu minus sigma squared s. And this means, well, like we can solve this again. So my function g is nothing else than affine function. So in time, it's just mu minus sigma squared times t plus g, which is a constant. So this is an element in our, we have to still find it. Right, so what I want is, okay, so my x is the solution if I choose f to be the exponential of sigma times bt, right, plus nu minus sigma half, square half dt, plus a constant g0. And now I have that, I need to have that, this has to be this, this g has to match my initial condition. So if I set here 0, 0, this gets 0. So what I need is x0 to be the log of 0, so that I have here x0 exponential of sigma times t dt. All right. So that's the solution of our simple linear differential equation. And this is here called, note, xt here is called geometric Brownian motion. Motion. And in mathematical finance is also called Black-Scholes model, because this is the process modeling the price evolution in the model used by Black-Scholes. All right, here we go. Okay, so let me give you a second example, which you then can solve yourself on the problem sheets, which is the Ornstein-Uhlenbeck process. Also frequently appearing model, not in finance, but that's what's anyway, here we go, Ornstein-Uhlenbeck process. Here the dynamic is given slightly different. So the dynamics dx is given by minus alpha xt dt plus sigma times bt, right? So we have an ordinary differential equation which is perturbed by some additive noise, because here the noisy part is not depending on the solution itself. And this is t, and this is equal. And this is just a constant as usual, and we have a parameter which is just supposed to be non-negative. Okay, again, this can be explicitly solved, and this process xt is just given by exponential of minus alpha t x0 plus sigma times the integral of exponential minus alpha ds ds dv. And that's your task to do to find the solution. Cheats. All right. There we go. All right, so these are two examples, and then you will see or discuss further examples on the problem sheets. But what we see here, I mean, these are both two linear equations. So they both, I mean, the coefficients are, okay, at least are fine in the solution process X. And this brings us in general to linear equation, because there one can still find an explicit solution. So in general, a linear SDE is of the form. So we have dx is given by alpha times, so alpha is a function in time, xt plus beta t dt. So this is the drift term, and now I have the volatility, the diffusion part, and this function phi, and then the function theta. Dt. All right. Okay, and well, to have everything well defined, so let us assume alpha, beta, sigma, theta are in H2 log. And x0 is a constant. Okay. The good thing about these linear ones, I mean, strictly speaking, a linear SDE means the coefficients are only affine, right? Because I mean, these are not linear functions; they are affine functions. The main point is that you can always solve this equation explicitly. This is content of the next proposition. So let me start a new page here. This is proposition 5.2. A solution xt t of the linear SDE. Okay, let's call it 5.2. Is given by that's xt. You can define the process to be x0 multiplied with the exponential of y, and I have to tell you in a minute what y is. And you have the exponential of yt minus ys times beta s minus mu s theta minus phi ds plus yt ys ds. right? Okay, and now, okay, I promised you I tell you what y is, so let me do so. Where t is given by the integral phi with respect to Brownian motion plus the integral of alpha minus 1/2 phi square. Yes, yes. Right. And if you, I mean, have heard like learned ordinary differential equation, you can check yourself. I mean, if you set phi and theta to be 0, I mean, this is just a fine ordinary differential equation, which you can also solve explicitly. And I hope you end up then with the same term as you get here. All right, so I mean, here, I mean, you see, I mean, the y and then the x are not, I mean, they're not a differential equation, right? The right-hand side is explicitly given here. So let me prove it. I mean, the proof is not too hard. It's just an application of Ito's formula. So let me check. I mean, so we only need to check that x here, as it is defined here, satisfies our linear differential equation. Okay. That's all we have to do. So let me first thing, to make my life a bit short, easier, is y. The exponential of yt I want to define with h. All right. And then I want to introduce a process zt. Which is x0 plus integral s h inverse, right? H is a positive process, so I can now divide by it. So this is 1 over h s. Yes, and theta. Yes, yes, plus g of h inverse divide 1 over h. Yes, dbs. Right. All right. And the thing why I want to do this is because now I can express x as is defined here, to be h times zt. Right? So I called labeled, I mean, this year's age, this year's age, and this year's age, and the rest, which is left over here, this is minus age minus age minus 1, 1 over h, and these are the rest terms. Okay. This is all I want to have done. And now I want to apply, I promise you I want to use Ito's formulas twice. I mean, let's use using Ito's formula for Ito processes. Wait, this was theorem 4.8 view. And what we know is that if you have an Ito process, right, and why is an Ito process? We can calculate its quadratic variation. Okay, so if you use this, what do we get? Well, h is okay. This by its definition, right? Y and y is an Ito process. You see here. Oh, sorry, y is an Ito process. So we can do so. This is 1, yeah, right? Minus. Plus. Sorry. T xt dt. Right, here we go. 1/2 xt ds. right? And now I use what I promised you here. So that's 1/2 of phi st, right? This is coming from y, and here this is just h. So I get my hs and dvs. And now I have here all the other terms. What do I get here? I get 1 sigma alpha h ds, because the rest, the other terms, they cancel. All right. So this is just the definition of y. All right, and now I use again Ito's formula. For x now, and x, oh, okay, well, how do I want to use it? Well, I want to use it for the product here. Of h and z. I mean, this is a product of two Ito processes, so I can also directly use the product rule, which you have had on the problem sheets. So what do I get? Is, right, just to remind you, the integral of h with respect to z plus the integral of z with respect to, and then I get the quadratic covariation of h and z. Well, now I plug in what I have learned here. So I know the of what h is. I mean, I calculated it here, so I can get it here something. Maybe give some more space. So what do I get? So this is just plugging in all the definitions. Sorry, here we go. ds plus theta dbs, right? Plus next term here, the h integral with respect to the h. So I get here z s h ds phi s dA plus h ds. And now I have still the covariation, right? This here, I mean, you can also look on the exercise sheet. This is nothing else than integral from 0 to t of theta times phi. Right? So what do I get here? So the last term is exactly this integral, which you hopefully have checked on the problem sheets. All right, and now I put everything together, and then I'm done. Right, so this is nothing else then. Okay, let's sort it out. So this is alpha times xt. Yes, right. This is x alpha times xt plus beta, which comes from here. ds plus, and now I put all these resting integrals together. Right, so that's nothing else than phi s dx plus beta s ds dbs. Right, and this is our linear stochastic differential equation which you wanted to solve. So indeed, the solution, the claimed solution, is a solution of the linear differential equation. Next time, in the next video, we will understand more general the stochastic differential equation, and in particular verify that the solution is actually uniquely determined by the differential equation, right? In this proposition, we only said, okay, there exists a solution which you can explicitly write down, and we're not going to verify that it's unique because we will do it anyway for a more general class of differential equation. All right, thank you for watching.